Assalamu alaikum everyone. Welcome to the 18th lecture of our numerical methods course, and this is the last lecture of this course. Okay, so let's get started. So the plan for today is to revisit two core concepts of linear algebra. I think you guys are already familiar with both of these concepts. The first of the concepts is the LU decomposition. Okay, so we are going to see what the LU decomposition is all about, and we'll try to solve an example. We'll try to decompose a particular matrix to its upper and lower triangular matrices. Okay, and we'll again try to revisit the concept of eigenvalues and eigenvectors. And I think you guys are already familiar with these two topics. We'll basically jog our memory about these two topics. Okay, and again we'll try to uh, take an example matrix and transformation matrix, and we'll try to find eigenvectors of that transformation matrix. Okay, and their corresponding eigenvalues as well. Right? Okay. So what is the concept of LU decomposition? Okay, so to put it very simply, if you have a matrix, you can separate that matrix, or you can factor out two separate matrix from that original matrix, and those two matrix will have two different properties. Okay, the first matrix will have non-zero values on its lower diagonal, or we can say that the entries along the diagonal and the entries below the diagonal will be non-zero. Okay, will it may consist of zero entries as well, but the entries above the diagonal, which is here, here, and here, those entries will for sure be zero. Okay, and and the case is the opposite for the upper triangular matrix, where along the diagonal we'll have non-zero values just like before, but below the diagonal we'll for sure have zero entries. Okay, so that's the essence of LU decomposition. We are going to take a matrix, and we are going to decompose it into its inherent lower triangular and upper triangular matrices. Okay, and what's the advantage of doing this? So you guys have already learned about Gaussian elimination back in your linear algebra course, right? So what did we do for Gaussian elimination? We tried to come up with an upper triangular matrix, right? And after coming up with that, so before that we made an augmented matrix, and after performing the Gaussian elimination, we basically deduced the equations, the resultant equations, and we tried to solve them using substitution, right? So suppose so our goal was solving ax equals to b, right? If you recall. So suppose you have multiple b's. Okay, so our goal is to solve for x, right? The x column vector, right? So if you have numerous amount of b's, so for a single b it's okay, you can perform Gaussian elimination once, right? So if you have a vast number of b's, and say for the sake of argument the matrix A that you have is very large. Okay, so what if you only resort to Gaussian elimination? You have to perform this Gaussian elimination step every single time, right? So for each column vector B, you need to perform the Gaussian elimination once, right? So which means if you have 100 B's, you need to perform Gaussian elimination 100 times, right? And say for the sake of argument, if your matrix A is very large, this Gaussian elimination will incur a huge overhead, right? Huge computational overhead, right? So that's where the LU decomposition comes into play. So what it does is it helps us to record the steps of the Gaussian elimination. Okay. So what does this mean? It will be clear in a bit, unless of course you're already familiar with this topic, which means you already know about the elimination matrices, right? So when we perform LU decomposition, we basically memorize, or we basically store the elimination matrices, right? Which basically tells us what the Gaussian elimination step did, right, in a particular step. So with the expense of a bit more memory, we are getting a computationally efficient solution of ax equals to b for multiple b's. Okay, and say if you have a large A as well, we are basically sidestepping a huge computational overhead, right? When we are using a decomposition, okay? And when we decompose a particular matrix into its lower triangular and upper triangular forms, we can basically solve those system of equations, those triangular system of equations, using forward substitution and backward substitution. So what does these two terms mean? We'll discuss them in a bit. Okay, don't worry about it. So let's try to solve this example. Okay, so given a matrix A, which looks something like this, we're going to decompose it into its lower triangular and upper triangular matrix. Okay, so let's go head on over to the bamboo paper and see. Let's try to solve it step by step. Okay. Okay, so the matrix that we have here is what? A equal to, let me see, it's what? 1 minus 2. So this example is from the lecture note. So in the lecture note it's given 1 minus 2 3. Then we have in the second row we have 2 minus 5 12, and on the third row we have 0 2 and minus 10. Okay, so this thing is our original matrix A. Okay, and our goal is to decompose this matrix into its inherent lower triangular and upper triangular matrices. Okay, so if we perform matrix multiplication on those resultant lower triangular and upper triangular matrix, we should get back our original matrix A. Okay, so let's do that. So okay, so we'll perform a simple Gaussian elimination. So what do we do? So we see that we, our goal is to come up with the upper triangular matrix at first. Okay, so in order to come up with the upper triangular matrix, we have to get rid of what? The first order of things is to get rid of this entry over here, right? So we need to get zeros at the lower triangle, right? So all entries below the diagonal has to become zero, right? So let's try to make this zero at first. Okay, so how can we do that? So notice that we have 1 in our first row, right? So in the first column, in the first row, we have 1 over here. So in order to make this entry 0, what we can do is we can multiply our first row with minus 2 and then add it to our second row. Okay, so let's say we are doing what? We are doing, say, R2 is equal to what? Uh, minus 2R1. So we are multiplying minus 2 with our first row, then we are adding it with our second row. Okay, so this is the transformation that we are going to do in order to eliminate this entry over here. Okay, I hope my cursor is being seen right now, unlike the previous lecture. Okay, so what happens? So our first row will remain as it is. We are not making any changes to our first row because it does not concern our upper triangular matrix. So now what do we have? So our goal was to make this to 0, right? So we have 2, which is being added with minus 2 times 1, right, which is minus 2. So minus 2 plus 2 is 0, right? So this thing becomes 0. Then we have what? Minus 2 times minus 2, which is 4, since minus minus becomes plus. And 4 being added with minus 5 is basically 4 minus 5, right? So 4 minus 5 will give me minus 1, right? So we have minus 1 over here. And then minus 2 times 3 is minus 5. Minus 5, oh sorry, minus 2 times 3 is minus 6, not minus 5, my bad. Minus 6, and minus 6 times, minus 6 plus 12 is what? 6, right? 12 minus 6 is 6, right? Okay, and we are not making any changes to our last row over here, so we'll keep it as it is. Okay, so 0 2 minus 10, right? Okay, so this thing is the matrix that we get after eliminating our entry at the 2 comma 1 index, okay, of the matrix. So if you recall, while doing LU decomposition, we had to keep track of our elimination matrices, right? If you recall from your linear algebra course. So when we multiply a particular elimination matrix with our original matrix A, we should get our eliminated version of our uh, matrix, right? So our elimination matrix had to be multiplied at the left side of the uh, original matrix, right? If you recall, so say if we have an elimination matrix, let's call it E sub 2 1, because we are getting rid of the 2 comma, because we are getting rid of the entry at the second row and the first column, right? That's why the notation is 2 2 1. And if we multiply it with our original matrix A, what we what you would get is this matrix over here. Okay, so now let's see what this E sub 2 1 matrix looks like. Okay, we'll keep this in our memory, we'll keep this in our record, so that we don't need to say, so that we don't need to perform Gaussian elimination every single time. Okay, so let's try to see how we can do that. So let's try to let me choose a different color. So, okay, now we are going to see what the elimination matrix E sub 2 1 looks like. Okay, so the creation of these elimination matrices are pretty simple, very intuitive. So what are we doing here? We are keeping the first row as it is, right? So the first row of the elimination matrix will be whatever we get for the first row of our identity matrix. Okay. So this simply means that we are taking one instance of row 1, 0 instance of row 2, and 0 instance of row 3 in order to get our final row 1. Okay, that's why 100 is here. Now for the second row, what did we do with the second row? We made some changes, right? So what did we do? We took minus 2 of our first row, so minus 2 times R1. We took one instance of our second row, right? So we took minus 2 times R1 and we added it with 1 times R2, right? And we the values of R3 had no did not partake in the final value in determining the final value of a row 2, final entries of a row 2, right? So the in this entry over here we'll put 0. Okay, since row 3 does not concern itself with the final values of row 2. Okay, now what did we do for row 3? In the case of row 3, we did not make any changes, right? So it will remain as it is. So we took 0 instance of row 1, 0 instance of row 2, and 1 instance of row 3. Okay, the original row 3, which is as it is. So this thing right here is our elimination matrix. Okay, so if we take this elimination matrix and if we multiply it with our original matrix A, we should get this matrix over here. Okay, now let's continue the process. Let me switch back to our black color. Okay, so let me draw the arrows there. There is not enough space to draw here, so let me curve the arrow a bit. Okay, so now what we can do? Now our next order of things is to, so if it were the case that this entry over here was non-zero, then our next goal would have been to make this entry non zero. Okay, but fortunately this entry over here is already zero, so we don't need to make it we don't need to basically perform another step of Gaussian elimination to make this zero. Okay, let us concern ourselves with this entry over here. So now we need to make this 2, we need to nullify this 2. Okay, we need to eliminate this 2, which means we need to convert this 2 to 0. Okay, so how can we do that? So one approach would be to take the help of row 1. Okay, so we can take row 1 instance of row 1 and add it with row 3. Okay, so what that would do is minus 2 plus 2 would become 0. But the pitfall here is that if I take notice that we have 1 in this entry right here, right? So if I take one instance of row 1 and add it with row 3, I would end up with 1 over here, right? So I cannot take the help of row 1 in order to eliminate this entry over here. Okay, so what other choices do I have? I can take the help of row 2, right? So, okay, how can we do that? So, we have minus 1 over here and we have 2 over here. So, I need to come up with minus 2 some way, right? So, with uh, somehow I need to come up with minus 2. So, how can I do that? So, why not multiply 2 with row 2 and then add it with row 3. So if I multiply 2 with row 2, I get minus 2, right? Because minus 1 times 2 is minus 2. And if I add it with row 3, then I get minus 2 plus 2, which is 0, right? So let's do that, okay? So let's do this over here. So let's do what? Uh, R3, our new R3 will be what? Um, 2 times R2 plus R3, right? So let's do that. So we are not changing our row 1 just like before, it will remain as it is. And for our row 2, we are not making any changes to our row 2 as well. So it will remain as it is. But we are making changes to our row 3, right, according to this equation right here. So what are we going to do? Say 2 times row 2. So the value at this entry is 0, right? So 2 times 0 is 0 plus R3. The value at this entry is also 0, so we get 0 over here, right? So 2 times 0 plus 0 is 0, right? Okay, so 2 times minus 1 is minus 2 plus the entry at respective entry at R3 at row 3 is 2, right? So minus 2 plus 2 gives me 0, right? And lastly, finally, what do we have? 2 times 6, which is 12, right? And 12 plus minus 10 is 12 minus 10, which is 2, right? So we end up with 2 over here, okay? So this is the resultant matrix that we end up with, our resultant upper triangular matrix, right? So notice that we have um, we have non-zero entries only at the upper half of the matrix, okay? All the entries below the diagonal have been nullified, right? Have been set to 0. Okay, so now the next target is to come up with the elimination matrix, right? So this time what did we do? We eliminated our entry at the third row and the second column, right? So uh, and let's denote our elimination matrix as something like 3 2, okay? Since we have eliminated the entry at the third row of the second column, okay? And what will this elimination matrix look like? So we kept the first row as it is, so we have 1 0 0 over here. So again, I'm telling you how to semantically interpret this. We take one instance of the first row, 0 instance of the second row, and 0 instance of the third row, which means the first row gets preserved, right? It was as it it becomes as it has been all along, right? So in our original matrix we had 1 minus 2 and 3. In our resultant matrix we will also have 1 minus 2 and 3 in the first row, okay? Fine. So let's talk about the second row. So notice that we did not make any changes to the second row as well, right? So I'm talking about this intermediary resultant matrix. Okay. So 0 minus 1 6, 0 minus 1 6 is the same as it was, right? So 0 1 0. Okay. Which means that we're taking 0 times the first row, 1 times the second row, and 0 times the third row. Okay. Which means the second row will remain as it is. Now let's talk about the third row. In our third row, what did we do? We took what? 2 times of R2 and added it with the previous R3, right? Previous row 3, previous third row, right? So how do we store that in our elimination matrix? We can say, okay, we took 0 times our first row, we took 2 times our second row, and we took 1 times our third row, right? By third row, I mean the third row of this intermediary resultant matrix, okay? And whatever I have found out after adding them all up, I got 0 0 2 in my new resultant matrix's third row, okay? So that's how you uh, keep track of the elimination matrices, okay? Now that we have all the elimination matrices at our disposal, and we have also seen that we have come up with our upper triangular matrix, which is this thing over here. Now we want to find out our value of L. Okay, L is the lower triangular matrix, right? So let's see how we can do that. So recall that what did we do with our elimination matrices? If we had our original A, we firstly we multiplied E sub 2 1 at the left of A, right? And we got something like this. Then again we multiplied E sub 3 2 E sub 3 2 at the left of both of these matrices, and we got something like this, right? Which was the upper triangular matrix. So this thing gave us the upper triangular matrix U, right? So how can we find out the value of L? So why not take all of these uh, all of these elimination matrices and take them to the left? Okay, left hand side of the relation over here. We will take it to the left. Okay, so what do we have? So we have remaining A at our left hand side, and if I take e to 1 to the left, I get e to 1 inverse, right? So the order will be switched, order will be flipped around. We have e3 to inverse, then we have u, right? So, and since we have by definition the LU decomposition gives us what? Two matrices L and U, which when multiplied together gives me A. We can say that okay, whatever whatever value of the matrix or whatever matrix that we get when we multiply the inverses of all the elimination matrices, that will give me my L matrix, right? So ultimately, if I multiply all these, if I multiply together all the inverse versions of these elimination matrices, of course in the order that I have specified over here, I should get A is equals to L U, right? So the lower triangular matrix is basically the multiplication of the elimination matrices, the inverse of the elimination matrices. Okay. So for this particular example here, let's try to see what the inverse of the elimination matrices together will look like. Okay. So one nice thing, one nice property of the elimination matrices is that when you try to calculate their inverse, you can simply flip the polarity of all the entries below the diagonal, and you will end up with the uh, inverse version. Okay, so for let's say for e21, our target is to find the inverse of e21, right? So what can we do? We can simply keep all the uh, entries along the diagonal and all the entries above the diagonal as it is, and all the entries below the diagonal that we have, we just flip their polarity. Okay, by flipping their polarity I mean if we have a negative value we convert it to a positive value, and vice versa. Okay, and by vice versa I mean that if we have a positive value we convert it to a negative value. Okay, so since we have a negative value over here -2, we're going to write 2 at this respective entry. Okay, so and 1 will remain as it is, 0 0, since 0 doesn't have a polarity, right? So 0 0 and 1. So this is the inverse version of my E sub 2 1 elimination matrix. Okay, and for E sub 3 2 we have what? E sub 3 2 we have, so we have 2 at this entry over here, right? So this will become -2 of course. So let's write the remaining entries at first. 1 0 0 0 1 0 and 0 -2 1. Okay, so this thing is our inverse version of our E sub 3 2 matrix. Okay, now if I multiply them together I should get something like what? So simply I can just, let me use a different color. So I should get a matrix that looks something like this: 1 0 0. I have 2 over here, so we just put the respective entries: 2 1 0. So multiplying the elimination matrices is also pretty simple. Okay, you just put the respective values at their respective places and you're good to go. Okay, so since I have minus 2 over here, I'm going to put minus 2 over here and 1. So what this is giving me is the L matrix, right? So now I have the U matrix and the L matrix at my disposal. So I can say that I have successfully decomposed my original matrix A to its inherent or constituent lower triangular matrix and upper triangular matrix. Okay. Now that I have done this example, let me see if I have, whether I have done this correctly or not. Let's go back to our presentation and try to uh, match the answers. Okay, so notice that we have a lower triangular matrix over here and an upper triangular matrix over here. Okay, so let's head back to our presentation. So we should get what 1, 2, 1, 0, minus 2, 1 in our lower triangular matrix, and we should get 1, minus 2, 3, minus 1, 6, and 2 in our upper triangular matrix. Okay, so let's head back and match our answers. Okay, so in our presentation, what do we have? For L, we have 1, 0, 0, nice, 2, 1, 0, nice, and 0, minus 2, 1, which perfectly matches with our answer. And for the upper triangular matrix, if we have 1, minus 2, 3, good, 0, minus 1, 6, 0, 0, 2, right? Okay, fine, it matches perfectly. So that's how you have, when given matrix A, you can decompose it into its constituent lower triangular and upper triangular matrix. Okay, I hope the process is clear to you guys. I think most of you already know how to do it, okay, from your linear algebra course. We are just basically revising the technique, okay, fine. So now that we know how to perform LU decomposition, let's talk about the last topic of this course, which is eigenvalues and eigenvectors, okay. So what are eigenvalues and eigenvectors? So if you don't remember what they are basically what? All the vectors in the vectors. So eigenvectors, what are they? Let's talk about eigenvectors at first, then we'll talk about eigenvalues. Okay. So eigenvectors, in layman terms, these are the vectors in the vector space which do not change their span after undergoing a linear transformation. Okay, so if you recall, when we had a particular matrix, that matrix had the capability of rotating or shifting the whole vector space, right? So these are very abstract concepts, very hard to impart in pen and paper, right? So the go-to video or the go-to playlist that every student watches to understand or visualize these abstract concepts of linear algebra is the playlist, The Essence of Linear Algebra by 3 Blue 1 Brown, right? So this GIF over here is taken from the eigenvalues and eigenvectors video of that playlist, and you can click on this link to watch that video. Okay, highly recommended if you have not already watched it. So let's say we have a particular uh, vector space that looks something like this thing over here, okay, and this pink color or purple color vector, after getting linearly transformed by a particular matrix, it gets knocked off its own span, right? So this thing is of course not an eigenvector, okay. But if you notice this yellow set of yellow vectors and set of green vectors over here, these set of vectors, so there are an infinite number of such vectors, right? These set of vectors, they do not change their span, okay. After undergoing the linear transformation, they are not changing their span or the direction, right? They're only getting squished or stretched. So in this particular example, they are all getting stretched, right? So the degree to which, or the scalar factor by which they are getting stretched, is called their respective eigenvalues. Okay, and these green colored vectors and these yellow colored vectors are called eigenvectors. Okay, since they are not changing their span. This pink color or this purple colored vector is not an eigenvector. Okay, since it's changing its direction and span. Okay, so the eigenvalue of this set of yellow colored vectors is of course 2, and the eigenvalue of these set of green colored vectors is of course 3, since they are getting stretched by a factor of 3, right? Okay, so let's try to mathematically understand how we can determine the eigenvector and eigenvalues of a particular transformation matrix A. Okay, so if you have a particular matrix, say A, let's say it's a square n by n matrix, then non-zero vector V is an eigenvector, and a scalar variable lambda is the eigenvalue of that corresponding eigenvector V if it satisfies this equality right here, okay, which is the matrix A times the vector V is equals to the scalar product of the variable lambda and the eigenvector V. Okay, so what is this thing telling you? So let's head back to our bamboo paper and try to understand it. Okay, step by step. Okay, so change. Let's go to the next page. Okay, so what did we see? We saw that the given transformation matrix A, when multiplied with our vector V, will give us what? Uh, Product, a scalar product, which is the product of our eigenvalue lambda with our eigenvector V. Now, what does this thing signify? Let me change the color. Okay, so it says that when this eigenvector over here, so this thing is of course an eigenvector, right? And this thing is our eigen. Oh, my handwriting is so bad. Eigen value, right? So it says that when this vector V upon being multiplied with the matrix A is undergoing a certain transformation, so be it a shifting transformation or a rotational transformation, whatever resultant vector that we end up with, it will be a scalar multiple of our original vector V. Okay, so our vector V will retain its properties, except for the fact that it will be either stretched or squished by a scalar factor lambda. Okay, whatever the degree to which it's expanded or contracted is denoted by the value of this lambda variable over here. Okay, we call this lambda our eigenvalue. Okay, so our eigenvalue basically dictates the degree to which our transformation matrix stretches or squishes our eigenvector. Okay, and what's our eigenvector? I'm reiterating again. Our eigenvector is the vector that does not change its span upon being transformed. Okay, fine. So another weird thing that you notice here is that this thing on the left hand side of the equation right here is a product between a matrix and a vector, right? But on the right hand side we are seeing a product between a scalar value and a vector, right? So let's try to reformulate this equation as something like this. Okay, so A times the V vector, and we are going to write our lambda in the form of a matrix. Okay, so how do we convert a particular scalar value to its corresponding matrix? We just multiply it with the identity matrix, right? So we end up with something like this. So this thing right here, let me draw it a bit more nicely. This thing right here is the same as writing what? The identity matrix where the diagonal has been set to the scalar value lambda. Okay, so this thing is the same as writing this thing over here. Okay, so now that we have this equation right here, let's try to take everything to the left hand side. We end up with something like this: A times V minus lambda I times V. Okay, which is equal to 0. So let's factor out the common part, which is uh, the V vector, right? So let's factor out this part over here. A times lambda I times the unknown eigenvector V will give me 0. Okay. Now, if you recall from your linear algebra course, I think it was in chapter 2 or the last part of chapter 1, I think. from Professor Gilbert Strang's book. So what did we do? We saw that if we had an equation that looks something like this, let's say ax, so x is of course a vector equals to 0, then me write it in another place. So let's say if we have an equation that looks something like this, a matrix A multiplied by a vector x is equals to 0, then we say that we have a non-zero solution of our vector x. So of course, if all the entries of our vector column vector x is 0, then this equation will hold true, right? So our job is not to find that solution, right? Our job is to find, or our goal should be to is to find a non-zero solution, right? So that the theorem said that this equation right here will yield a non-zero solution, or the entries of our column vector x will be non-zero if and only if our, so in order to make this non-zero, our uh, matrix A, the matrix that we are multiplying the column vector with, it had to be singular, right? Singular is, let me write it over here, SIN So our transformation matrix A has to be, sorry, not the transformation matrix, the matrix that I'm multiplying with in order to get the value 0 for our unknown vector x. We say that that matrix has to be singular in order to get a non-zero solution for this equation right here. Okay, and if you also recall further, for a singular matrix A, so let's say if A is singular over here, the determinant of A is 0, right? So if I have a singular matrix, there was a theorem that said that the determinant of that matrix is 0. Okay. So now that we have this, now I would like to shift your attention to this this equation over here. Change the color. We have what? We have a particular matrix over here times a particular unknown vector v, and we have 0 on the right hand side, right? So this thing roughly resembles this equation right here, right? So from whatever we have discussed so far, we can say that, okay, if this equation if this equation needs to hold true, our determinant for the matrix over here, this matrix over here, so the determinant of A minus lambda I has to be 0, right? So instead of denoting determinant like this, we can simply say that the determinant of A minus lambda I is equal to 0. And again, let me expand it a bit further. Let's say if we have, let's say if our A, if it looks something like this, I'm going to use some dummy symbols. Let's say A, B, C, D. Let's say it's a 2 by 2 matrix, an example matrix, something like this. We said that our A minus lambda 1 would look something like this, right? A minus lambda, B, and C will remain as it is. We have D minus lambda, okay, which is equal to, of course, 0, right? So we also know how to calculate the values of determinants, right? So we'll, in a bit, in a few minutes, we'll solve a particular example and it will be clear to you guys, okay? So the long story short of the eigenvalues and eigenvectors is roughly what I have discussed so far. Okay, so in our linear algebra course, we went a bit more in depth, right? But for this course, this amount of superficial knowledge is enough, okay, for this course. And another thing, another terminology that I'd like to point out is that this equation right here, this equation that says that the determinant of A minus lambda times I will give me 0, is called the characteristic equation. Okay, characteristic equation. Now Why is it called the character? Why is the solution to my characteristic equation called the eigenvalues? Because the word eigen is a German word. Okay, so the etymological background of this word is from the, it has its origin in the German lexicon. Okay, so the word eigen means what? It means property. Okay, property or characteristic, property, characteristic or quality. Okay, things like that. In Bangla we call it বৈশিষ্ট্য. Okay. Uh, so from this root word eigen, so this German word eigen, it says whatever equation that we end up with, the equation whose solutions give me the eigenvalues, that equation is called the characteristic equation. Okay, since it's giving me a characteristic or a property of the original matrix A. Okay, fine. And just as I have said, the solution to this equation, or the lambda values for which this equation holds true, are the eigenvalues of my matrix A, and for each of the eigenvalues that I get, the values of V, or the versions of the column vector V that I have over here, all those V, all those possible, or all sets of the vectors V that satisfies this equation right here are the eigenvectors of the matrix A. Okay, and again by eigenvectors I mean the vectors that do not change their span, or do not change their direction upon being transformed. They only get stretched or squished by a particular scalar factor, and this scalar factor right here is called the respective eigenvalue of that eigenvector. Okay, I hope the concept is very clear now. Okay, so let's try to solve an example. Okay, let's go back to our presentation and see what example we can solve. And again, before moving on, I obviously encourage you to watch the video that has been so beautifully made by 3 Blue 1 Brown. Okay, okay, so let's move on. So this is the final example that we are going to work with in this semester. So this is this small 2 by 2 matrix 1435. Okay. So instead of going through all these mathematical jargon, let's try to solve it in our bamboo paper. Okay. So the matrix is for 1435. Okay. Let's head back to our bamboo paper and see how we can come up with the eigenvalues and eigenvector of this particular matrix. Okay, let's do that. Okay, so let's go to the next page. So our, if you recall, our matrix was what? A equals 1, 4, 3. Let me write the 4 a bit more clearly. 4, 3, and 5. Right? Okay. So let me change the color to black. Okay, so now our target is to find out the eigenvalues and eigenvectors. Okay, so we are going to write what? So we have seen that we need to come up with solutions for this equation right here. Okay, a minus lambda I times the vector v is equal to 0. So all the vectors that are going to satisfy this equation right here is going to be our set of eigenvectors. Okay. So before finding the set of eigenvectors, we need to find the set of eigenvalues, right? So we have seen that for this equation to hold true, we needed our matrix at the left side over here to be singular, right? And singular matrices have a determinant of 0, right? So we can say that A minus lambda I is equal to 0, right? So what does a minus lambda I mean over here? We know our we already know what our original matrix A looks like. So let's write down the determinant. We have what? We have 1 minus lambda I is what? 1, right? So in the diagonal entries of our identity matrix is all 1, right? Are all ones. And if we multiply lambda with them, we get just lambda itself, right? and 4 will remain as it is because in that corresponding entry in the identity matrix we had 0, right? So 4 minus 0 is 0. Again 3 will remain as it is because in that corresponding entry of our identity matrix we had 0. But in the fourth and final entry, what did we have? So in our original matrix we had 5, and now we have to subtract lambda times 1, right? Lambda times 1 because we have 1 in the final fourth entry in our identity matrix. So we have 5 minus lambda times 1, which is lambda. Okay. So this is our determinant over here. We say that this determinant must be equal to 0 for this equation to hold true. Okay, so let's try to calculate the determinant right now. So this thing there will be an option over here. Okay, so the determinant calculation is very easy. So we are going to what we are going to do. We are going to say, okay, let's consider this thing over here. So we have 1 minus lambda, and we have remaining 5 minus lambda, right? 5 minus lambda. So I hope you guys remember how to compute determinants, right? We take a particular entry, we discard all the entries in the determinant that is along the row and along the column of the entry that we have considered, and all the remaining entries we multiply the determinant of all the remaining entries with the entry that we have considered, right? So then we have remaining what, this entry right here. So let's consider the entry 3. So discard everything along this row and along this diagonal. We have only remaining 4, right? So let's write. So we have minus. So since we are considering the second entry, we have to put minus, right? For each, so before each even indexed entry, we are going to have to put minus 1 before it. Okay. So we have minus 3 times what, 4, right? 3 times we have 4 remaining 4. This whole thing is equals to 0. So this thing is our characteristic equation. Okay. So let's try to expand it a bit further. We have 5 minus lambda minus 5 lambda and minus minus plus lambda square, right? Then we have 3 fours are 12, which is equals to 0. Okay. So let me draw a line here. Then whatever we have remaining is what, lambda square. Let me write the 2 a bit more clearly. Lambda square. Then we have what, minus 5 lambda and minus lambda gives me minus 6 lambda, right? We have minus 12 plus 5, which is minus 7, right? This thing gives me a quadratic characteristic equation, right? Which is lambda square minus 6 lambda minus 7. Let me write the lambda a bit more nicely. Minus 6 lambda minus 7 is equals to 0. Okay. Now let me use my calculator and find out the roots of this quadratic equation. Wait a bit. Okay. Okay, the roots are lambda is equal to, shows me 7 and minus 1. Okay, so these are the roots of my characteristic equation. So these roots are of course my eigenvalues. Okay, so let's call them lambda 1, and let's call this lambda. Okay, so we are going to get two different sets of eigenvectors for each of these, uh, for each of these two eigenvalues. Okay, fine. So let's try to find out the set of eigenvectors for lambda 1. Okay, so for lambda, let me switch back to the black color. So let's write for lambda 1 is equals to 7. What do we have? We have in our determinant, in our original equation, we have in our matrix 1 minus 7, right? Because we have the entry 1 in our original matrix. We need to subtract lambda times I, okay, which means 7 times 1, which is 7. 4 will remain as it is. 3 will also remain as it is. But in our fourth and final entry, we have to write 5 minus 7, okay. This whole matrix times a particular vector gives me 0, right? Fine. So how do we solve this thing over here? Let me simplify it a bit more. So this thing is what 1 minus 7 is minus 6, of course. This thing is what 4. We have 3. 5 minus 7 is minus 2. Okay. This thing is, sorry, times v gives me 0. So our target is to find the value of the column vector v. Okay. So so for what value of p will this matrix so for what value of p when multiplied with this matrix right here will give me 0. In order to find that, we need to perform, if you recall, we needed to perform Gaussian elimination, right? Or Gauss-Jordan elimination to be more precise. So let's do that. Okay. So in order to perform Gaussian elimination, the first order of things was to form an augmented matrix, right? So the augmented version of this matrix would look something like this: minus 6, 4. We have 0 on the right, then 3, minus 2, and 0 on the right. Okay. So this is my augmented matrix. Okay. So let's perform Gaussian elimination on this matrix right here. So if you recall, before even proceeding to the steps of our Gaussian elimination, we can see that if we just try to get rid of this entry right here, we automatically get rid of this entry as well, right? Why is that the case? Because the first row and the second row are dependent, right? The second row is basically a multiple or integer multiple, multiples or an integer multiple, a multiple of our first row, right? They're basically equivalent, right? So if I multiply the, so if I say, okay, my new row 2 is equal to what? Um, half times row 1. So half times 6 will give me 3. And half times minus 6 will give me minus 3. And then I add it with my entry in the second row, which is 3. And we end up with 0, right? So I'm basically eliminating this entry over here. But upon doing that, what I'm doing is that I'm eliminating this entry as well. So in our second row, in our last row, we are getting a series of zeros, right? So it ends up looking like something like this: minus 6, 4, 0, and we have 0, 0, 0, right? So what does this say about our resultant matrix? It says that whatever equation we form using this first row over here, let's go over to here for more space. So whatever we have over here is what? Minus 6x plus 4x gives me 0, right? So we can have an infinite, sorry, not 4x, 4y, right? Y. So there are an infinite number of solutions to this equation right here, right? So any value of x, any pair of values for x and y which satisfies this equation is a valid solution of this equation, right? So we can say, okay, why not use 6 for 20, 6 for the 24, right? So let's say what the value, let's say the value, if we take the value of x to be say 2 and the value of y to be 3, so what do we get? Minus 6 times 2 is minus 12. So let's say this is 2 and this is 3, right? What do we get? We get minus 12 plus 4 times 3 is 12, right? So this gives me 0, right? So we can say that 2 and 3 is a pair of valid entries for my column vector v, right? So any pair of valid xy values can be set as the corresponding entries of my V matrix. Okay, V row vector, column vector. Okay, so we can say that okay for our eigenvalue lambda 1, we get a eigenvector that looks something like this. Okay. Fine. So is the set of eigenvectors finite? Of course not. If I use any other scalar multiple of this vector over here, I'll be able to satisfy this equation, right? So if I have, say, if I take 4 and 6, which is what you get after multiplying this column vector by 2, you get 4 and 6, right? So minus 6 times 4 plus 4 times 6 will obviously give me 0, right? So any scalar multiple of this vector is a possible eigenvector. Okay, fine. So you can say any scalar multiple of v1 is a possible eigenvector that corresponds to the eigenvalue lambda sub 1. Okay, which means all those sets, all the eigenvectors present in that set get stretched by a magnitude of 7. Okay, by a factor of 7 upon undergoing the transformation that is applied by multiplying with this original matrix right here. Okay, fine. So now that we have done it for our lambda 1, let's do it for the lambda 2 as well. So there is not enough space right here. Let me erase this arrow. Say whatever I did. It's okay. Okay. So for lambda 2 is equals to what? It was minus 1, right? So for minus 1, what do we get? Um, so our matrix would look something like this. 1 minus 1, 4. So 1, sorry, 1 minus minus 1, right? So it will give me 1 plus 1. Then we have 3 and 5 minus minus 1 will give me 5 plus 1, right? So this is my uh, matrix which when multiplied with my eigenvector v would give me a value of 0, right? So let's go to the next page. So we have what? 2, 1 plus 1 is 2, we have 4, we have 3, then we have 5 plus 1 is 6, right? Very cool. So yes, 2, 4, 3, 6. Okay, so 2, 4, 3, 6. So this is my matrix, and when I augment it, it would look something like this, right? I put zeros on the right hand side. So let's perform Gaussian elimination on this as well. And if you look closely, in this case also, we are getting what? We are getting a set of rows that are dependent on each other, right? So the row 2 right here is of course a scalar multiple of row 1, right? So 2, if I multiply the first row with if I multiply the first row with say minus 3 by 2 and then add it with the second row, I should be able to eliminate what? I should be able to eliminate all the entries in my second row, right? So let's do that. So let's say my new row 2 would be my 3 by minus 3 by 2 times R1. So for 2 it would give me minus 3. For 4 it would give me what? Minus. So 2 by 4 is 2 of course, and minus 3 times 2 is minus 6. And minus 6 plus 6 would of course give me 0, right? So minus 3 by 2 times R1 plus R2. That would be my step of the Gaussian elimination. And I would get something like this. 2, 4, the first row will remain as it is, and for the second row we have 0 0 0 all the way through, right? Fine. And from this augmented version over here, augmented matrix, we have the equation 2x plus 4y is equal to 0. And again we are seeing that we have an infinite number of solutions for this equation right here, right? So what we can do is we can come up with a particular valid pair of xy values that basically suffice or satisfies this equation right here, and then we can say that that pair of xy values is a valid set of entries for my eigenvector v2. Okay, so we can say that okay, v2 vector, so the corresponding eigenvector that I'm getting for lambda 2. So recall that for lambda 1 I got what v1 vector, right? So for the lambda 2 I would get v2 vector, which is which consists of entries that are valid xy pairs. Okay, fine. So what can we do over here? We can say that okay, if I take the value of x to be uh, minus 2 and the value of y to be 1, I should get what? Minus 2 times 2 is of course minus 4, and 4 times 1 is plus 4, right? So minus 4 and plus 4 basically nullify each other, and we end up with 0. So minus 2 and 1 is a valid pair of values for my uh, for satisfying this equation right here. Okay, so we just plug them into our corresponding entries for our v2 eigenvector, and we can say that okay, whatever scalar multiples of this vector right here that we have will be a valid eigenvector of my initial transformation matrix A. Okay, which means that any the set of vectors that I get from this v2 vector right here, they will not change their span or their direction after being transformed. Okay, after undergoing linear transformation, they will only get uh, magnified by a order of minus 1. So what do we mean by getting magnified by, or getting scaled up, or getting stretched by an order of minus 1? We by an order of minus 1 we say that okay, it's not getting magnified in actuality because the factor is 1, right? So instead of getting stretched or squished, it is as it is was before. So the length will not change, the vector's length will not change. Instead, its direction will get flipped around, right? So say if we had a particular vector that was something like this, it would be what? Upon being transformed, the span of the vector would remain as it is. So let's say this thing over here, let me change the color. So say that the span of my original, so let's say this is my v vector. Okay, so v2 vector to be precise. So this is of course the span of this vector right here, right? And upon being transformed, we say that the vector will obviously get flipped around, right? Yeah, about the origin, it would get flipped around, but the length of the vector will remain as it is. Okay, so this is my v2. Let's call it v2 prime. So this is my v2 after being transformed. Okay, or after undergoing the transformation that is facilitated by my original matrix A. Okay, so we say that our length of the vector, the stretching or squishing of the vector is not being done. Instead, the direction of the vector, so by direction I mean that the point at which the vector is pointing is getting flipped around, right? So instead of pointing from the origin to this northeast direction over here, it will now point to the southeast direction, okay, with respect to the origin. So this is what, in essence, the eigenvalues dictate. The eigenvector says that okay, this minus 2 comma 1 vector that we have, this vector will not change its span upon being transformed. Okay, so this black version of the vector is the non-transformed version, and this blue colored vector that I have drawn over here is the vector, the eigenvector after undergoing the linear transformation facilitated by my original vector A. Okay, so I think this is the answer. Let me go back to the slide, the presentation, and try to match the answer and see whether what I've done is correct or not. Okay, so for lambda 1 we got 7, for lambda 2 we got minus 1, very good. And for the vector, the eigenvector v1 we got 2, 3, nice. And we also got what for minus 1 for lambda 2 we got phi2 as minus 2 comma 1. Alhamdulillah, very good. Now we can of course verify and check whether the answers that we have gotten are correct or not. What can we do for doing that? We can multiply that eigenvector with our original matrix A, and whatever resultant vector that we would end up with, that vector will for sure be a scalar multiple of my eigenvector. Okay, so for example, they got 14 and 21 as the resultant vector, right? And we can say that 14 and 21 is a scalar multiple. This vector, right, it's a scalar multiple of this 2 3 vector, right? So if we multiply 2 by 7 and 3 by 7, we end up with 14 and 21, right? So a factor of 7 has been, so we can say that this v1 got stretched by a factor of 7, right? So this 7 was our lambda 1, our eigenvalue, right? Again, if I multiply minus 2 1 that I got as my value for v2, we see that we get a value which is 2 and minus 1, right? So how do we obtain 2 and minus 1? We just take whatever vector we have and we flip it on the exact opposite direction. Okay, so the opposite vector of minus 2 and 1 is of course 2 and minus 1, right? So if I multiply again, if I multiply minus 1 with my eigenvector over here, I get minus 2 and 1, right? So we can say that this eigenvector over here gets uh, gets doesn't get stretched or squished. It just gets its direction changed. Okay, but its span remains as it is. Okay, fine. So we can say this minus 1 that we got was the second eigenvalue, right? Lambda 2. Okay, I hope that you guys understood this eigenvalue and eigenvector. Okay, fine. And that's the end of this lecture. And with that, we have ended at the we have come to the end of this whole course. Okay, see Math 4543 numerical methods. So it was nothing short of a honor and a privilege to teach you guys whatever I have taught in this course. I hope you guys could at least learn up, at least understand a part of what I was blabbering about all throughout this semester, and I hope something or some concept that we have learned throughout this course gets or what can I say is returns to help you at some later point in your life. Okay, be it in your thesis or in some part of your project that you are working on. Okay, inshallah. And if you have any question about this lecture or any other lectures preceding this lecture, you can of course contact me through email, messenger, or WhatsApp at any time. And yeah, that's it from my side. uh, I enjoyed teaching you guys. Hopefully it was likewise for you guys. Fine. So assalamu alaikum warahmatullahi wabarakatuh.